Welcome to public lecture of Stardust Star project. My name is Sergey Gordeev. I'm member of coordinating team of the project, and today I'm very pleased to introduce our lecturer, the Professor Mirel Birlan, who is going to talk about the meteors, meteorites, and their parent bodies. But before he starts, I will ask him to maybe introduce himself and talk about his career and why he's interested in this area. So, Mirel, please, you can start.
Thank you, Sergey. So I am very pleased to be in front of you for this public lecture for this Stardust Technical School. And I will talk about meteorites, meteoroids, and their parent bodies. So I am a native Romanian. I've started my education here in Romania, finish university, and then after a few working experience, I was hired in the Astronomical Institute of Romanian Academy in 1991. So last millennium. This was the beginning in the research as astronomer, and then I've started working for a PhD thesis. And at that time, it was very interesting to find new horizons and new ideas, new topics. And I found a supervisor in Observatoire de Paris, actually Meudon Observatory, and I've started a PhD thesis in astronomy in solar system studies, physics of asteroids, actually. And my supervisor was Antonella Barucci from Paris Observatory. And I was into a wonderful team led by Professor Andre Braic. And this team had a premonitory name, Europa. So like Europe. So I am one of the PhD students who finished on Europa team. Then in 2000, I've started a new career in France. I was hired by the National Center of Scientific Research. So I am now in the Institute of Celestial Mechanics and Computing the Ephemerides inside Paris Observatory, and also associate to Astronomical Institute of Romanian Academy. So this is to do something very short and brief, for the time being, I will try to talk on this topic, which is related to my main field, minor bodies or small, very small bodies inside the solar system. Actually, I am more related to the planetology, but on my field of activity, I was dealing also with dynamics and dynamical problems, and also with some statistics on small bodies of the solar system. I will start by defining.
Excuse me, Mirel. Before you start, I would like to say a couple words about the rules. So everyone familiar with the rules online, so please keep your microphones muted. If you have any questions during the lecture, please either send them to the chat or leave them till the end of the lecture. Then we will have time for questions and maybe some discussion if necessary. So sorry for interrupting. So the microphone and screens are yours now.
There is no problem, Sergey. Thank you. So I will start by defining my my subject: meteoroid, meteors, and meteorites. So this is the something which is quite normal and usually when an object which is smaller than 5 meters, you can consider it as a piece of rock or something like that. You can consider it in the solar system, and in the solar system you have a lot of objects, and also on this size range you can have also such kind of object. There are less important than the asteroids, and they are however important to interact with the atmosphere of our planet. So here you can have a sketch on what it happens when what happens if an object, an asteroid in this case, graze our planet. And here you have the image of the asteroid 2012 DA14, which was passing very fast and very close to the Earth. You can see here on in green the orbits, let's say the generic orbit of geosynchronous satellites, and you can see that this object is passing between the Earth and the geosynchronous orbit, and this happens very fast. So you can imagine that this object can release also, like in the bottom left, a lot of particles. So if this object will be disintegrate, you will have a lot of interaction between such kind of particles, such kind of pieces, such kind of rocks, or whatever you have, with the atmosphere. For sure, you will have some particles which will interact with the atmosphere of the Earth. They will be captured by the gravity of the Earth. And what will happen? It happens. You will have something like a flash, a piece of light, a segment of light on the sky, which will be which you call what it will be a meteor. So in the first case, we are talking about the meteoroid, something which is outside in the interplanetary space, and the interaction will produce something which is called a meteor. And sometimes when the piece of matter is very important, we will have a large, let's say, flash, what we call usually a bolide or a super bolide. So obviously, such kind of bolide or super bolide corresponds to an important mass of meteoroid. When you have this object which interact with the Earth's atmosphere, you will see that almost 95% of this object will become energy, heating or lighting energy, and only 5% of the material globally will hit the Earth. And this is just for the massive meteoroids. So most of the time, meteoroids are vanished into the atmosphere, just let's say, heavy meteoroid with important masses will arrive. Some remnants will arrive on the Earth. And here you have some examples of meteorites. Every piece of interplanetary material which fall down on Earth is called meteorite. And here you have an Alma Ata Theta meteorite, which was found in Sahara Desert. And here you have a Saturn piece of meteorite. And here you have the newest one, the Vinci Combi meteorite, which falls this year on February 27 in United Kingdom. So meteoroid is outside the atmosphere of the Earth. Meteor is the light interaction between the interplanetary material with the atmosphere, and meteorite is what we have, what we can collect from the ground. I will talk about this in a context. How can we? How do we know? How can we hunt such kind of pieces of interplanetary material? So we will construct networks of observations. Here you have on the upper right, you have a movie of several cameras, all sky camera, which recorded the same event. These records allow us to make a triangulation and to find the ellipses of falling. This event that you will see here in the movie was obtained in the frame of a network. You have it here on the map, called FreePwn. This network contains more than 210 stations, and now we have 150 which are daily working. Some of them are running out, and some of them are reinstalled, and so on. We have components on 7 countries, and also we can also record some echoes from a transmitter. You have most of these cameras installed in France, but you have also in Italy a huge part, Prisma. You can see also in Romania 11 stations. You can see also that Canadian colleagues installed also their own network based on the same technology. But as I said, you have also cameras from the same network in United Kingdoms, in Netherlands, Belgium, Switzerland, Germany, and so on. How they look like, the whole sky camera. It's a very, very simple device, which are working sometimes in a very, very harsh situation. Here you have the camera after a thunderstorm in Pic du Midi at 2,800 meters of height. And this is the camera inside the dome. And this allows us to record events. Here you have a statistics of such kind of events for more than 4 years, the last 4 years. Statistics based on more than 3,700 events obtained at least by two stations. Why two stations? Because we need to have a triangulation and to find the path of luminous event. And as you can see from the graph here, there are a lot of events each month. You can see that at the beginning you have less of events because the deployment of the network was not ready, and you can see that the deployment was very, very important in 2019, and we have a lot of events. In the blue bar represent the sporadic meteor, while the black lines you have here represent the meteors which are recorded and related to what we call the meteor shower. So if you will count the year 2018, 2018, you will see that there is a huge number of events comparing to the other one. So we have an increasing number of events. Then we have a stable number of events in 2020 because the deployment was almost at this level, 150 cameras. The statistics that we have now, it's seems is represented here, and why we are doing this? Because we are interested to know how much matter, interplanetary matter, interact with the Earth yearly, and this this could be seen also by the number of events, but also by the number of important events, masses of meteor associated to meteor. So you can see here Perseids, Geminids, Quadrantids, and so on. A lot of meteor shower. We identified the object, but also we can see a lot of sporadic meteors. And on the color legend, you'll see the speed of such kind of object, starting from 10 kilometers per second up to 80 kilometers per second. And you can see that on this map, Perseids are, as we expected, high velocity objects, while objects from this you can, if you imagine, you will see here a sinus line, the ecliptic more or less. You can see that here you have a lot of blue dots, which means that the velocity of such kind of objects are very are relatively low. So for sure, if you are looking to such kind of map, you will expect to have something. You will see a dichotomy in terms of velocities, and the statistics of orbits obtained from Freepon and published in 2020 show us that we have dynamically two categories of matter. Those related to the inner objects. Here is the main asteroid main belt, and the other category is related to objects coming from Neptune and beyond, the comets of short period. So we have a quite important distinction. This is the orbit of the Earth, one, and on the x-axis you have the one over semi-major axis and the number of meteors. What it is very interesting also, it is the fact that the statistic doesn't contain interstellar meteoroids. You have here the position of extrasolar object Oumuamua, which comes from the outside, which is the origin is outside the solar system, and you will see that you have almost no population of in this category of orbits. So why we are studying meteoroids and asteroids? Why not? Because we have such kind of situation, and you'll see a falling star during the summer. It is very fun. You will see the Perseid. But what happens is, if the size of such kind of body, it is very important. In this case, you need to be able to quantify how the Earth will be let's say the probability to have a collision with an important meteoroid. And when I said meteoroid, I will said something bigger than 10, 12 meter of diameter. So you can see here in this graph on the left that you can have an annual event of about 20 kilotons. Here it is Tunguska. It is quite important and a local event. You can have also something which happens, let's say, each 100 once per millennium. And also you can have in this map situation on which this is one every 1 millennium, yeah, and this is every 10 millenniums million years you can have a global catastrophic event. When you are looking on the right side, you will see that Freepon, our network, will cover this part, which is still unknown. We know some objects which were interacting with the Earth. Here, the meteorite Alma-Ata Sita, it was the first one who was collected, because we knew that an asteroid 2008 TC3 will hit the Earth. So the asteroid, the major part of the asteroid vanished in the atmosphere, and some particles, some pieces were collected on the Sahara Desert. Then you have here Chelyabinsk, the famous one, and we were living with this event. Then I was living also with an interaction between Jupiter and the comet Shoemaker-Levy 9, and also we are also now we are exploring an important object which belongs to the category of potential hazardous asteroids called Bennu. Well, I was saying at the beginning of my talk that I will talk in terms of interrelationship between meteorites and let's say try to explain where they are coming from. And for sure, you need to explain how we can refill such kind of meteoroid shower or a sporadic meteor. How can we produce such kind of small pieces? For sure, in this situation, we are dealing with several components, namely asteroids, comets, maybe interstellar planetary dust, or interplanetary dust. Why not? Because we are in the neighborhood of the Earth. We can have meteors, but just due to the entering in the Earth atmosphere of space debris. So all these are interconnected, and I will try to give you an overview of such kind of big picture. So the key question is which parents are related to which meteorites. And if you are looking to the Museum of Natural History, if you are counting all the meteorites on the Earth, you will find something like I don't know, 60,000 objects. You will find something like that. You have a lot of objects, more than 75%, which are what we call an ordinary chondrite composition. Then you have a small part, carbonaceous chondrite, and also you have a part called achondrites, which actually are melted objects. So evolved, mineralogically evolved objects, stony irons, and also irons. So the question is which parents are related to which meteorites. And if you are cutting and you look on the polarized light, you will see something like that on the meteorite. You will see something which is quite interesting at the level of microns. You will see that we have something like spherules or something like that, bigger, less important. You will see that there are fragments of spherical pieces. These are called chondrules, and inside chondrules you will have a lot of small and different pieces of mineral which were formed actually very early in the very early stages of the formation of the solar system. So when we want to know, we want to have information about the formation of the solar system, you need not just to look at the biggest object, but also to the smallest one. The most important is to find ways to have an answer of such kind of cosmogonical problem. So meteorites will give us the chemistry of the early solar system, and also studying pieces of material coming from the interplanetary environment. You can have the clock of the early solar system, how the solar system formed. How can we do this match between the meteorites and some other objects? Well, usually we are looking to some dynamical aspects. You are looking to some let's say to the oscillating elements, and you will try to find metrics in order to mix, to put together dynamical elements of meteoroids and also dynamical methods of possible parent bodies. And what we can do is it's a paper signed by Bogdan Dumitru in 2017. You'll make some tables like this one using some kind of metrics. This is a metric of 5-dimensional space, and using these metrics, you can see how you can match a parent body with a meteoroid or meteor. And you can see here, for instance, you have here a work done for meteor shower. You can see here that for this meteoric shower, you have a parent body, a comet. But also you cannot accept some asteroids as parent bodies. You can have even on the literature, you will see also asteroid as parent body, also comets, and also a mix between asteroids and comets. So it is very hard to answer to one question: how relevant, how true is this relation? Why? Because we have a difference, an important difference. Comets are disintegrated, and it is normal to see something just the tail, the dust, and also pieces of comet when the comet vanished when it is close to the sun. And in 10 years, 15 years ago, Dave Jewitt from University of Hawaii at that time had an idea to look at what we call now active asteroids. Why active asteroids? Because in this case you have somehow transition between objects, asteroids, which are not developing coma or tails, and comets, which are developing in space a tail or several tails. So up to now, in 2019, he found more than 30 active objects, and this becomes a subject of survey inside the main belt of asteroid. You can see here, for instance, the main belt of asteroid. You have here the orbit of the semi-major axis of Mars. You can have here the semi-major axis of Jupiter, and you'll see that there are a lot of objects which were identified in the main belt of asteroids. So you have a sketch just on the right side of this transparent. Then I will try to give you some hints why we are still looking for evidences how asteroids could be parent bodies of meteoroids. And here you have a sketch, a picture proposed by Morbidelli et al. In 2009. And at that time, on this sketch, you will see that for objects with diameter larger than 100 kilometers, Morbidelli stated that these objects are objects, let's say, monolithic with low porosity and let's say a segregation into several layers. And while for the objects smaller than 100 kilometers, you can have a high macroporosity and more or less a rubble pile structure. The science advanced, and this could be a general rule, but however, we can still, as the science advanced, we can look at larger objects, and what we can see here is are let's say images obtained from the ground with a very large telescope and a sphere, an adaptive optics instrument, and you can see here some of the major object in the main belt of asteroids, Sirius, the first one, and also you can have here an object, Hygeia. And if we are looking to all these objects, we will see that Hygeia, it is quite spherical and with no craters on the surface. So this may suggest that Hygeia, it is in a hydrostatic shape equilibrium. So for Sirius, for instance, which is quite spherical, we know that the size of Sirius could explain this shape because of self-gravitation, while for Hygeia, we don't have such a mass which can change the structure of Hygeia, unless if you propose a hydrostatic equilibrium shape, and this may suggest a reaccumulated object. So we can have also rubble pile structure of larger object. This is not the case for all the objects, but you can have exception. Rubble pile asteroids are represented here. We have actually two space missions which were launched and observed two near-Earth objects. One, Hayabusa 2, which was going to an asteroid called Ryugu, a 900-meter in diameter, and also Osiris-Rex, which was launched for an object, let's say half of size as Ryugu, called Bennu. And you will see that the shapes of this object are very, very similar. It's something like a rhombic shape with an equatorial ridge and a lot of boulders on the surface. And this suggests that we have at two objects of two, which are more or less rubble pile objects. So it is very, very interesting, because if you are going deeper into the science of Osiris-Rex, you will see that NAVCAM, one instrument of Osiris-Rex, records 3 times something like evidences of mass loss. You can see here some bright points just near the shape of Bennu, and this record, such kind of records occurs several times, and they are correlated with the late afternoon time of ejection. So particle size are estimated to be in the size 1/8 centimeter. So it is very, very interesting, because Bennu, it is not an active asteroid. It is an object with no activity. So very, very interesting. And here you can have also two images, two movies of sample collection, sample records from Bennu and from Hayabusa. And this is very, very important and exciting, because in this case we will have let's say, non-contaminated matter coming from the surface of these objects, these two objects. And we can study their structure and also the composition on the laboratory on Earth. So in December last year, the sample of Ryugu was collected from the Australian desert, and they have started working with this kind of material. They found at least 5 grams of material. You can have here the sample catcher, and they have 5 grams of materials. You can imagine the importance of such kind of mission when you know that one of the main goal was to collect samples from an asteroid and bring them to the Earth. Also, scientists from Hayabusa participating to the Hayabusa 2 mission found that the gas inside the sample catcher is a gas from Ryugu. This gas has a composition other than the composition of the Earth atmosphere. Also, in this case, we are for sure we need to answer the question: which are the mechanisms who can explain all this disintegration? And you can see here some of mechanisms: sublimation, rotational instability, breakup, and here you can have also a limit of Rubble spiral. So you can just split the object because it is Rubble pile. You can have also impact. You can have also a variation in temperature, which can fracture the material, a desiccation stress, and also electrostatic effects. While for asteroid classes, we can pass now to the let's say to the analysis of samples in the laboratory and also via telescopic observations. So when you are observing asteroids in the visible and near infrared using a spectrograph, you'll see something like that, an alphabet of asteroids. You can do statistics, and you can have a lot of classes. It's, let's say, as an analogy with someone who is very, very interested by birds, and this person wants to classify birds because of their neck, because of their color, because of their leg, and so on, and wings, and so on. So we are on the same situation, and what we are doing when we are dealing with a spectra of asteroids, we will try to see, to find, and to catch a taxonomic system. I mean, you'll utilize a method, a mathematical method, and you will use also a complex of mineralogical behaviors in order to establish a correspondence between the physics, the mineralogy, and also the what you are obtaining via telescopic observations. And we have a lot of problematics, but first, one of the first problematics, we will call it comparative planetology. And in this comparative planetology, we need to compare something in the centimeter size with something with information which was obtained from a body like that, 18 kilometers in size. So you have a challenge such as the scale factor, such as the signal to noise, and also the light source and experimental condition. There are a lot of challenges. So I will try to explain here How much time left, Sergey?
We don't have any limits for the time, but I think if we aim to finish in 1 hour, that would be
okay. So
50,
I will
50
try
minutes.
to be quick. Here, when we are talking about mineralogy and also the spectral behaviors of minerals, we need to go and to see from the cosmochemical representative of minerals. And we know very, very well that the most important and the spectral signature that we have are from silicates, because they are more representative in terms of minerals over almost all the universe. So we will look for pyroxenes, we will look for olivines, and also we need to look in several ways, because we can find a lot of impurities inside the matrix, and this will change the profile of spectra. So for sure, for now, for building such kind of taxonomic system, we know that, for instance, olivines are very, very close to the stony iron meteorites, while the iron meteorites are very, very close to such kind of taxonomic classes. While basalts, so heated and also melted materials, are very, very close to the V-type asteroids, and carbonaceous chondrites are very, very close to the C complex of meteorites. So in this case, we can fill some puzzle into our taxonomic system, but this represents more or less than 25%. So what about the ordinary chondrites? And this is what in the literature we call the ordinary chondrite conundrum. The largest part of the meteorites, ordinary chondrites, do not have explicit relation with an asteroid taxonomic class. And this could be explained just by the process of space weathering. So an object from the interplanetary space is all the time into a harsh condition. You have a solar wind, cosmic rays, you have, let's say, collision with small bodies and so on. So the surface will change the spectral signature. So we will try to fix this, taking into account all the space weather mechanism. So I will skip this because this means what I said previously, the space weathering, the sum of processes that act on body exposed to the harsh space environment. And also we will try to mimic this space weather with in the laboratory. And there are laboratory experiments which can change the profile of olivine, for instance, because the irradiation could create the nanophase iron particles, which are changing the profile of olivine, for instance. Here you have the profile non-irradiated, and then you will see that the spectral bands are very, very shallow. So we can have here also a relation between the complex of silicates with the one of ordinary chondrites among meteorites. Relevance of asteroid taxons, it is not obvious, because you have some taxonomic class among the asteroids which are not representative inside the sample of meteorites. For instance, this one and this one, and so on. And how can we explain this? This could be explained if we are looking not to the asteroid, but most of the time to the IDP, interplanetary dust particles. And if you are looking here, we will change the scale. Here you have the scale between 8 microns and 14 microns. And you can see that the models can mimic very, very well, can fit very, very well the structure of IDP. This is a reflectance, this is a emission spectra, not a reflectance spectra as in this taxonomic system. So yeah, I think for the moment I can put. I think I still have one transparency, one slide before after this. So the meteorites could be related either to comets, to asteroids, or interplanetary dust particle. For interstellar dust particle, it is quite difficult. For the space junk, I haven't read here. So in summary, conclusion on meteoroids, meteoroids are a complex body, need complex investigation, meteorites records, asteroid samples, cometary and IDP collection, and these allow us to have a big picture on the origin, evolution, and also give hints of solar system formation. Thank you.
Thank you very much, Mirel, for very interesting talk. At least you made quite a few surprises for me. But now it's time for questions. If anyone in the audience have a question, please go ahead, just unmute your microphone and ask the question. Okay, while people is thinking about the question, I will ask
I don't have a question. Oh, please.
Go ahead, Katalin. Yeah.
Thanks, Mirel, for this very nice talk. Very nice presentation. Very nice talk, and a lot of information and a very good overview in the field. Can you make a comment about the risk of the meteoroids in the near space? What kind of risk they impose on the constellation of satellites in terms of the, say, functionality in the near future? If how much impact will produce a collision with a fragment of which travel with such large speed of around 80 kilometers per second, if I recall exactly the speed of Perseids. Can you make a comment or more details on these aspects?
Yeah, I can talk a little bit about some aspects related to services concerning meteoroid showers. There are predictions for avoiding collision between meteoroid shower, meteoroid stream, and the space missions. And I know that space agencies are very, very interested to have such kind of predictions. Then this is an aspect, and the other aspect is that I haven't mentioned this. Perseid, for instance, when you are looking to the Perseid during the month of August, you will see a lot of events, but most of them are very, very, they are vanished into the atmosphere. And this is mostly because you will have particles from fluffy and also less weighted material coming from the comet, the parent body of this meteor shower. And as far as I remember, there is no evidence of object meteorite from this meteor shower. So most of the time, these energetic particles are vanished into the atmosphere. They are not falling on the ground. The risk could come from an object which is coming mostly from the neighborhood of the Earth, even if the velocity is not very, very important. So yeah, it is for instance, Chelyabinsk was not predicted. And as far as I remember, at that time, we were looking to another object, and which was predicted to graze the Earth. And at the beginning, there was speculation that both the object which falls on the region of Chelyabinsk and the other asteroid were related, and there was no relation. If you are looking the trajectory of that object, and if you are looking the trajectory of the asteroid falling on Chelyabinsk, there is no dynamically relation. Yeah, I don't know if my answer was
yes. Yes.
I think it was an extended answer. So,
okay.
Yeah.
Any other questions from audience?
Yes, I would like to. Hello, Mirel, it's Christoph. Thank you for this very nice talk. I like it a lot, working on the interplanetary dust particles also. A very good overview, and I like a lot also that you mentioned this interaction with space weather and so on. So just as a follow-up question to Katalin, in fact, it's not only the danger of this kind of objects. I think that also in space missions that should measure plasma and magnetic field and electric fields, the interaction of these dust particles with the spacecraft potential, with the spacecraft itself, that may lead to changes in spacecraft potential and so on, should be avoided, and they destroy, let's say, these high frequency measurements. So it's not only the danger, but it's also that they destroy the reliability of measurements in space. So did you think about that direction also?
Thank you, Christoph. I'm very glad to see you with this during this school. Yeah, it is very, very important what you are saying, and I agree. I fully agree that such kind of interaction could distort the measurements. But I think the most important is how can you avoid such kind of situation, because you cannot interact with all the particles. You will have most of the time a simulation, and you will see how the particles will be spread, and also how the particle will evolve on the using a lot of mechanism of their drifting in their object, drift in their orbit, and most of the time the satellites will be in a safe mode position and also in the safe mode functioning. If you have a provision, if you have ephemerids on which you can predict a surge in the activity, and the Earth, which will pass at that time in this region, for sure, the safest mode is to try to switch off the instrumentation, for sure. Yeah. I don't know if my answer is fine for you, but I don't have other answer.
Yes,
Yeah.
it is. Thank you.
More questions? Guys, don't be shy. You have our experts in front of you. Go ahead with your questions. Okay, then I will ask my question. It's just to check one of your estimates on one of the first slides. You said it's about 20 kilotons of matter coming from the sky per year. Is it an estimate for the amount of material reaching the surface of Earth, or is something different?
I think you are. I will look on my presentation. I think you are talking about this.
Yes, annual event 20 kilotons.
Yeah.
Does it mean it's this amount?
No. It is not the global amount of matter. Into a network, you can estimate a global amount of matter, but this is just how often could you have an event, just one event, not a total amount of matter. Okay. And also here you have on the bottom right, you will have also the estimation of the sensitivity of Frippon in this let's say this is a relative simple sketch, and here you have it. You have something more elaborated, and Frippon will answer just to question related to at least to object not larger than 1 meter in size.
So does it mean if the objects are smaller than 1 meter?
Smaller, yeah.
Probably nobody count these events. Is correct?
Yeah.
So, but do you have any estimates for the global amount of stuff falling down from sky on us?
Oh, well, we have experiences. Actually, we have the Earth experience something like that. If you are looking to the Barringer crater, you will see that this was created by, so 1 kilometer in diameter was created by 1.2 kilometer in diameter, was created by an object with a metallic object, of course, with or a metallic majority metallic object, not less than 8 meter in diameter. So it is a very, very small object. But usually when your estimation is around 50 meter in diameter, you will expect to have some damages, local damages, a lot of local damages. So for the object which was at the origin of dinosaur death, the estimation, if I have a good memory, was more than 100 meters in diameter.
Mm-hmm. But as you say, it's a plenty of small particles falling with unnoticed, essentially.
Yeah.
So, but I guess the risk is still relatively low because, for example, I'm living on this planet quite a while, so I never experienced this. But saying that, recently on the UK TV, there was in the BBC News, there was a small object, maybe a size of
here. You have it here. And and actually this was the second meteorite observed after the records on Freepon data. Yeah, and this is a wonderful story because the rest of the object fall on the street, so it is easy to find, and also this is a wonderful science because for this object you have not only Freepon network but also desert fireball network, which contribute, also the autonomous all sky network from United Kingdom, and also the clouds radars. I mean the meteorological radars of United Kingdom. So it was a lot of let's say effort, and successful effort, because it is a carbonaceous chondrite, not very easy to have it. So yeah.
Good. So, any more questions? Then you have a last one from me. When I was preparing the advert for your lecture, I made a picture of Meteors shower. So I took my own photograph of San Sebastian, a town in the Spain, in the Basque Country, and then I was using a Photoshop, just draw some meteorite. And at some point I thought, should I put them parallel or they should come as like from single point? Can you?
It depends on size. I mean, you will see that there is a gradient for the meteor shower, so there is a convergence. But if you'll observe a small part of the sky, you can consider as a parallel on the small part of the sky. Yeah. Okay. It is a good question. Yeah, it's a question of perspective.
Yeah, because I had a few minutes to think about whether I should make them parallel. Okay. Anyway, thank you very much again for a very interesting talk.
You are welcome.
Your time, and the last chance for the audience to ask the question.
Mirel, I would like to thank you for the talk.
Ciao, Massimiliano.
I think we are going.
Thank you so much.
I think we are going to see each other next week.
Yeah, for sure. Okay. Yeah.
Thank you again for your very interesting talk.
Okay, thank you very much for Mirel, and thank you much for audience who was very patient, and they had all day of lectures and then spent at least 1 hour with us here in a public lecture. Thank you very much.
Bye-bye.